Hi, I'm Beth Wilson. I'm one of the hosts of 730, a television program produced at the National Air and Space Museum for middle school students. Today on What's New in Aerospace, we will be discussing the experimental X-59 aircraft, currently designed to fly faster than the speed of sound and reduce the loudness and intensity of a sonic boom. Our guests today are Nils Larson, Armstrong Flight Research Center lead NASA test pilot for the X-59, Alexandra Loubeau, Langley Research Center co-lead for the X-59 community testing, and Ray Castner, Glenn Research Center for the propulsion lead for the X-59. Thank you all for joining us today. I want to remind everyone who's watching right now that we are going to be taking questions from you all. So be sure to put your questions into the comment section, and we will get to as many of them as we can. Also, let us know where you're watching, and we may give you a shout out. We're going to start today. I'm going to ask Nils. I'm going to start with you. Nils, can you give us an overview of the X-59 project?
Sure. Right now, you can't fly supersonic, or you're not allowed to fly supersonic over the United States unless you're a government airplane or have special permission. And the reason is because of the sonic boom that is produced. So the purpose of the X-59 is to go out there, and we think we can, and we know actually, that we can design an airplane to produce what we call a sonic thump instead of a sonic boom. Something that's much quieter and it's not as displeasing of a sound as the sonic boom. So the big thing that this airplane is going to do is it's going to go out and get the data so that we can reset that regulation, so that we can have the noise, the regulation based on noise and not necessarily based on just don't go faster than Mach 1. So that's the basics of it. And let me know if you want me to go into more detail on the different phases, or if that's good.
That's good for right now. I'm sure we're going to get a lot of more questions about the program. Alexandra, can you tell us exactly what is a sonic boom and how do you plan on reducing it?
Sure. So a sonic boom is what's created today with today's supersonic aircraft. As it flies faster than the speed of sound, you end up with shock waves close to the aircraft. It's due to the nose, the canopy, the tail, different aspects of the aircraft. And all these shock waves, as they travel from the aircraft to the ground, they end up merging, and you get one shock at the front and one shock at the end. And that's the boom boom that you hear from a sonic boom. And it can be a loud and startling sound, which is why supersonic flight for civil aircraft is prohibited over the US and really over most of the world. For the X-59 and other future aircraft, if you're able to actually shape an aircraft, you can prevent these shocks from all merging as they travel to the ground. And so you end up with a smoother sound that we like to call a sonic thump that would be less annoying and a lower level sound.
Ray, you were designing the engines for this. How is the engine design going to affect the sonic thump?
Sure. So what we've done is we've bought the GE F414 engine to integrate into this airplane. That's an existing engine that's used in the Navy F-18 Hornet. And when I talk about the engine integration for sonic boom, I guess it'd be great if we could look at one of the pictures of the airplane, because everything on the airplane affects how the engine operates. So this is perfect. This is a picture from one of our wind tunnel tests, which I can talk about later if there are questions. But the engine sits on top of the airplane. It sits behind the really long nose is the biggest feature on this airplane, where the pilot sits. And then it sits over the top of the wing. And the wing, we really use the wing to shield the shock waves that are generated off of the inlet for the engine. And that really is the secret to engine integration for reducing sonic boom. And then just one last feature on the back end. You can't see it in any of these images. Probably there's a deck that sticks out behind the nozzle, and that also shields the shock waves off the nozzle from propagating to the ground and contributing to the sonic boom.
Nils, as a test pilot, do you want to tell us a little bit how you're getting trained up to actually fly this airplane?
Sure. One of the things that we're doing right now, and as a test pilot, we're involved with the design of different pieces of the airplane, especially when it comes to the cockpit and how we're going to interact with the aircraft, with the avionics on the system. The other pieces that you'll see is the flight control system and how the airplane flies. So we'll be in the simulator, like you can see here, where we'll practice some of the stuff in the simulator and give feedback to the designers so that they can improve how the airplane is going to fly, how it'll feel to us essentially when it flies, and the stability of the aircraft. And then eventually we'll work in some of the different emergency procedures that we'd be able to experience in the airplane, or could experience, so that we train up for that. We'll actually train to land the airplane, even though it's not a full motion sim, as best we can in the simulator itself, because it's only one person in the airplane, and the first time it goes and flies, and that'll be the Lockheed test pilot, Dan Kanan, that goes out and takes it out there first. No one's ever flown that airplane before, the first time he goes out and flies it. So the sim is very important for us to train in before we go get in that airplane. And we'll use that same training to help train the control rooms and a lot of other aspects for training, and not just the pilots.
We've got a lot of people watching from all over: Alberta, Canada, the Czech Republic, Wisconsin, New York, Illinois, Florida, Pennsylvania, Michigan, Texas, and Ohio. If you're watching, again, be sure to put your questions in the comments section. We'll get to as many of them as we can. And our first question is, how does it work for a project like this, where you're spread out all over the country? How do you coordinate to work on this one big project? Alexandra, let's start with you.
Okay. Yeah, I think we could all have something to say. So yeah, I mean, that's a great point. It's a project that reaches across many different centers at NASA, and we've been doing this for quite a while. We, in the past, before the pandemic, were able to travel to see each other, to have several project meetings, but we always have tag ups and meetings every week with our project management and the technical leads, and with our various groups to ensure that we stay in touch. We have done a lot of background research testing together as a larger team, and those have been really, frankly, a lot of fun. I don't know, Nils, do you have some additional things you want to say about it?
Very good summary. Even like you said, even before the pandemic, we're always working across all the different areas. One of the interesting things from the pandemic, I think we're actually sometimes more connected because of, all the different platforms we have to connect when it comes to it. One of the things we found in the simulator was, and we probably wouldn't have thought of this, but we have flight controls engineers, across the country, whether they're at Langley or whether they're the Lockheed Martin people that are in Fort Worth, Texas, or whether they're people at home here in Palmdale, California. One of the things we found is I could go get in the simulator and put my simulation and up on, we used Teams at the time, and they could watch me do the simulation from all over the country, potentially all over the world, and ask me questions directly. So if I made a comment and they'd want to know more about it, they could, follow up in that question. And I don't know that that's something we would have necessarily thought to do, but because the pandemic kind of drove us to do it, it was very interesting. And that's something that we want to carry on in the future, because we get great feedback, and everyone, like I said, across the world can actually be involved.
Ray, do you have anything to add?
Yes, I agree. Much like Alexandra said, we're spread all over the country. The propulsion team has been working with, GE in the Boston area. I'm in Cleveland, NASA Glenn. We have folks out at Armstrong in California. Also, the Lockheed team is also in California. before the pandemic, we did some traveling. We were fortunate to be able to do most of our testing before the pandemic shut down. So the engine was ready to go. But, we've also learned to work online with each other on the various platforms. And also we've been running the simulator for propulsion simulations to provide input to the test plan. So it's very similar. And I think there has been a lot of learning along the way.
We have a lot of people watching from South Africa, Finland, Alabama, Maryland, Georgia, and some of your friends at NASA Ames Research Center are also watching. Nils, this next question is for you, and maybe you can do a comparison to somebody wants to know, when you fly a plane going faster than the speed of sound, how does it feel when you pass through the sound barrier?
Well, most of the time you don't even know that you passed through the sound barrier. It's not as exciting as some of the movies you may have seen make it look or sound. I mean, it was back then when they were trying to do it the first time because they really didn't know what to expect. But for us, the biggest thing you notice when you go through the speed of sound is you'll see the altimeter jump. And there's different reasons for that. Most of the time it's shock wave that's probably moving across the static ports on the airplane that feed the altimeter, and that's why it jumps around. But the other time you can actually see it happen or notice something that's slightly different, and that's when you go to slow down. And if you were to say go into a turn like with a fighter aircraft or something like that, if you went into say a 3G turn or a 4G turn as you were slowing down, one of the things that can happen depending on the size design of the airplane is as you pass through the Mach 1, as you slow down, what'll happen is this kind of weird where the lift, where it kind of is on the wing of the aircraft moves, whether you're supersonic or subsonic. And when it moves to subsonic, it kind of makes the airplane pitch up just a little bit more on some airplanes. So what you'll end up having is if you were holding a nice 3G turn, it might spike up to 3.5 Gs or something like that. And you feel it kind of dig in a little bit. But most of the time you don't notice whether you're going through the speed of sound one way or the other, especially if you're in level flight. There's times that, when I used to teach students in the Air Force, that when they went, they weren't supposed to go faster than the speed of sound, but they accidentally go faster than the speed of sound and not even realize it.
Alexandra, this next question is for you. Somebody wants to know, why are sonic booms such a big deal when flying over populations?
So this goes back to some research that NASA and others have done for the past 60, 70 years on some prior community tests when NASA was able to fly some supersonic aircraft over the community. The sonic boom really was an annoying factor. It just startles you, and if you don't see the airplane coming, you don't know to expect it. And so that is why it's banned across the US. You could imagine if you heard 10 of these a day, maybe you would not be so happy. But for what we're talking about with the X-59, these sonic thumps, and this is a great graphic for it, are just so much quieter. So those sonic booms from military aircraft or something like the Concorde, they're much louder. They're up there with very close by thunder, maybe fireworks. And as you kind of move down the scale towards the left, you start to see some softer sounds like hand claps or basketball bounces or distant thunder. And that's really where the X-59 sound sits. It's more like distant thunder or a car door slam from your neighbor's house, that kind of quality. And the sound is over in very quickly, in less than half a second. So these sonic thumps, we believe, would be much quieter and less annoying, but we really do need to gather the data from communities to understand how different people perceive that sonic boom sound or sonic thump sound. And the idea behind all of this research is to collect that data of everybody's perception and provide that to the aircraft noise regulators in the US, but also internationally, because they're hoping to make an international rule to allow civil supersonic overland flight.
I live near an airport, and the engine noise, where you sort of get used to it, it's still noise, So a sonic boom, I would not want to hear. Ray, how do these engines? How will they compare with an engine on a commercial jetliner?
So the X-59 is using a single engine. This is a military derivative engine, right? It serves with the Navy on the F-18. As most people are probably aware, the military engines tend to be smaller and have much higher performance, whereas the commercial engines, for a variety of reasons, fuel efficiency and noise, they tend to be much larger. They provide a lot more thrust. And they're just designed for a very different mission. So this engine is designed to go fast. It has the afterburning capability on the back end, and that'll help the X-59 achieve the Mach 1.4 speeds that we're looking to get to.
Nils, the next question is for you. Someone would like to know, what are the stall characteristics? How will the airplane handle slow flight?
That's a great question, and it looks like a dart, and there's a reason it looks like a dart, but we really don't want to get it too slow. The only reason we want to get it to be slow is to be able to land it. So the big thing is we aren't really going to take this thing to a stall, because that would be a bad day if we take it to a stall. So the big thing we're using is a digital flight controls. We're going to limit the amount of angle of attack that we have, so that we can't get too slow to actually stall the airplane. So we're going to use the advanced flight controls, or the digital flight controls, to keep us out of the area so that we won't actually stall it.
We still have time, so if you have questions, please put them in the comment section. We'll get to as many as we can. We've got people watching in British Columbia, Canada, Indiana, and Virginia. Our next question is, I'm not sure who this would be for. Would eventual possible electric aircraft be able to go as fast as the X-59?
That sounds like a Ray question. Tag, you're it.
Sure. I mean, I'm not really sure that there's a clear answer to that. There is a lot of research going on in electric airplanes. I think electric airplanes, as far as, to my knowledge, are going to excel on short haul routes, but it's not outside the range of possibility that some electric technologies could maybe make it on board supersonic aircraft for takeoff, landing. I mean, I'm making it up a little bit, but who knows what the next 40 or 50 years will bring once the electric technologies take over.
Alexandra, does altitude have any effect on the boom?
Sure. As that sonic boom sound is traveling from the aircraft to the ground, it does evolve. And so, as I mentioned before, with these shock waves merging or not merging, that the sound that you would hear would depend on what altitude you are, how far above the ground you are. Now, for the X-59, we'll be flying pretty high, above 50,000 feet, and so our predictions, our simulation tools all tell us that flying around those altitudes, the sound that you hear at the ground will be this sonic thump that it's been designed for.
Lula has a question. How many sonic booms can happen in one flight? Nils, do you want to take that one?
Yeah, well, it's kind of interesting in that, the sonic boom, once we go faster than the speed of sound, then the sonic boom is happening anytime we're faster than the speed of sound. We're kind of dragging it across the ground as we go. So the way we have this designed for our eventual phases is that we will probably accelerate and go faster than the speed of sound twice. So in our flight, the flights won't be very long, maybe an hour and a half long, maybe at most. But the idea would be that if you were in the same spot in the ground, you'd hear me go by once, and I'd turn around, you'd hear me go by the second time. So our plan is probably not to do a whole lot of them each time, just because I don't have the gas to do it.
Someone would like to know, and I'm not sure who this is a good question for. Could this improve noise reduction for stealth aircraft?
That's probably an Alexandra question. Here, I'll throw you under the bus this time. Feel free to toss one at me, next week.
Yeah, I'm not sure. I mean, if we're talking about supersonic aircraft, from the technology that we know today, if you're flying supersonic, you will create one of these sonic boom type sounds. And we're trying to reduce that to this sonic thump. And where we are with this X-59 demonstration aircraft is really the lowest that we think we can achieve with the shaping of the aircraft. I don't know if others have any additional comments.
Yeah, so I think it depends on when you say stealth, are you talking, obviously stealthy in that it will be quieter so that from that side you don't hear whatever is coming. I don't really know whether if you're talking about like a radar signature or something like that, I don't have a good feel for whether, that shape would have anything to do with that. That's, something you'd have to, I'll go find a different expert on that.
So, yeah, somebody asked, didn't we do this 55 years ago? And I guess the connection would be is like, how will this plane compare to the Concorde?
I guess I could take a stab at that. So, the Concorde was a great technology innovator, but it was not built for low sonic booms. It did create a loud sonic boom, and that's why it did not fly routes supersonic over land. Its routes that were supersonic were all over water. So one of the popular routes, I think, was New York to London. And the X-59 is really meant to demonstrate the technologies of being able to lower that boom so that you could fly over land without having an annoying sound. And so there are some similarities in the shapes, as you see in these photos, this kind of longer nose than the swept-back wings to allow for the supersonic speeds. But there are a lot of details that have gone into the design of the X-59 that are enabled by a lot of the computer resources that we have today. All the simulation tools have really advanced over the past couple of decades. And we're able to optimize the shape and the design for a low boom, but also for stability of the aircraft and various factors all at once. And that's how we've been able to design something like this that's new.
We still have a lot of people watching from all over: Liberia, Ontario, Canada, Oklahoma, Washington, D.C., Oregon, California. If you're watching this right now, remember you can share this video on your own Facebook page. Ray, our next question is for you, and it is, why do you use a wind tunnel to study these models?
Sure. So, wind tunnel testing is definitely an important part of developing any aircraft these days. We use a lot of tools, right? We use wind tunnel testing, we use computer-aided analysis, and then we use flight testing, and they all work together to kind of certify an aircraft to fly. In this case, this wind tunnel test was very important for this program because it assessed the inlet compatibility. It's very important to know that we have smooth airflow coming into the engine for all flight speeds. The engine does not like unstable air. It doesn't like interruptions in air. And there's a history of a lot of programs in the past have definitely had some issues with airflow, and we've learned from those. So we have methods that we follow in the wind tunnel to make sure that we can assess that our engine is airworthy to fly in this airplane. And one of the tools we use is the wind tunnel, and like I said, we also use computer analysis. And then finally, the final step will be flight testing. All those work together to assess the airworthiness of the engine in the airplane.
Alexandra, does the sonic boom noise on the ground increase with the aircraft speed? For example, is going Mach 2 louder than going Mach 1?
Oh, that's a good question. It's not a simple answer to it. It depends on many different factors, but essentially if you're flying at different Mach numbers, you may be flying at different altitudes. And so that goes back to one of those previous questions. Where the sound could be different depending on your altitude, but it also could impact a larger area. If you're flying at a higher speed and a higher altitude, you may have the sonic boom impacts a larger region. And so one thing maybe we haven't talked about yet is that the sonic boom is not heard just underneath the aircraft. There's a region of 20, 30, 40 miles wide where this event can be heard, and it may vary across that region as well. So that region could be larger if you flew at a higher speed.
Nils, someone is asking about the book behind you, Wood, Wire, and Wings. They want to know about that book. What can you tell us a little bit about that?
Well, my wife this is her office, so I borrowed it. But she's a children's author, and the book Wood, Wire, and Wings is about Lillian Todd, who is the first woman to design an airplane back in about 1910, I think it is. So, like I said, she's a children's author, and that's her. I think it's her first book.
So since we're talking a little bit about books, and we know we've got a lot of students watching, are there any books that you all would recommend for this audience about, so they could learn more about airplane development or supersonic flight? Is there anything off the top of your head that you can think of? Well, maybe not.
I'm trying to think. NASA has several publications. It really depends on how, those are really written more as a technical thing, where it's, more for, college and above, that kind of, describes that. I'm trying to think of I know there are some that are out there, but I can't think of what they are, that would be for, this audience for, middle school, even though I have, 2 middle schoolers, in the other room. But I can't think of any offhand that they have. If I come up with it, I'm sure I can add it on later or something like that and give it to you. But
that's
I know that there are some out there because, when I'm at the Air and Space Museum and I'm shopping there in the gift shop, those are the things that I'm looking for. So, it's the books to bring home for my kids.
I believe there is a NASA book that is about a flight test that NASA did with DARPA more than 10 years ago now, maybe 15 years ago or so. And that was about this shake sonic boom experiment. That might be, one reference we could pass by you.
Mm-hmm. Yeah, I know there are some books, specifically about like Dana Purefoy, one of our test pilots who retired recently. But, 20 years ago, there was a book on being a test pilot and that kind of thing. But, on airplane design, I know that there are some that are out there, but I just can't tell you what they are offhand. Yeah, I should help my wife and have her. Maybe she knows.
You can always check the National Air and Space Museum website. We're still selling books online, but it's been a while since I've been in the museum. Mm-hmm. Someone would like to know, and I think I'm going to ask this of everyone, but Nils, how does one become a test pilot for NASA? And are test pilots just pilots, or are they engineers as well?
If you're specifically a test pilot, yeah, you're an engineer or a scientist or a mathematician. You need to have a technical background generally to be a test pilot for NASA. There are test pilots out there in the world that essentially were pilots and then gained the technical background just through working at, say, a contractor or something like that. I've met some that are some of the best test pilots I've ever worked with that didn't even have a college degree, but that's pretty rare. So for NASA, we have we call research pilots and then research test pilots, or at least at Armstrong, where I work, we do. And generally, the research pilots, they can be pilots with almost any background. Most of them usually have a technical background that I described before. And a lot of those pilots will fly what we call some of our platform aircraft that go out and do a lot of the science research that you'll see out there, looking into climate change and that kind of thing, or maybe flying new sensors that may go on a satellite or that kind of thing. The research test pilots have a test background. Almost everybody that I can think of that works in our office from that were test pilots previously in the military. It's not required that you were in the military, but in order to be a research test pilot, we're looking for you to have been a test pilot somewhere else before you get hired. Long ago, like back in the 60s, there are like Neil Armstrong, who our center is named after, did not go through a test pilot school. He was a military aviator and also an engineer that came to the center and worked there. Fred Hayes is another test pilot that worked at Armstrong. He actually did go to test pilot school before he became an astronaut. He was a test pilot actually for, I don't know if he started with the NACA or whether he started with NASA. And then he ended up, while he was at what is now Armstrong, they sent him to test pilot school. Then he came back. It's a great education. There are test pilot schools both in the military, and there are test pilot schools that are civilian test pilot schools. Those are pretty pricey, but if you can find somebody to pay the bill, then, hey, go for it.
Alexandra, how did you get interested in the work that you're doing now?
Oh, yeah, sure. So I actually have a music background. I studied music engineering at the University of Miami, but that really got me interested in understanding sound in general, and how it's created, how it travels through the air, and how do people hear it and perceive it. So I followed that up with some graduate degrees from Penn State in acoustics. So there's an actual acoustics program. It's one of the first ones in the US. It's sort of a niche area, but there are people who come from physics, mechanical engineering, electrical engineering type backgrounds, a lot of musicians as well. And you'll see that at NASA, in our acoustics branches, it's quite a diverse set of folks from these different backgrounds. I first started researching on sonic booms when I did a postdoctoral fellowship, and that was in France at the Sorbonne University. And that's how I got interested in this problem and was able to start my career at NASA after that.
And somebody now wants to know what musical instrument you play.
I play the violin, and I'll give a shout out to the local orchestra that I play with. It's called Symphonicity, and it's made up of several amateur musicians from the area. At least two of them are also NASA acousticians.
Ray, what about you? How did you get interested in engine design?
I graduated as a mechanical engineer from Syracuse, and got to work for what was NASA Lewis, which is now NASA Glenn, right out of college 30 years ago. I started at the Aero and Acoustic Propulsion Lab. We were reducing jet noise, so I was a wind tunnel test engineer doing jet noise reduction. From there, I went over to our full-scale propulsion systems lab. It's NASA's only full-scale jet engine test facility. And we were doing high-altitude engine performance studies for unmanned air vehicles. And then from there, I went into the inlets and nozzles branch, started doing research on propulsion effects for sonic boom, specifically how the jet plume affects sonic boom. And then, definitely wanted to work on X-59 and was selected as the propulsion lead. It's a great project, but sometimes you just sort of your career just evolves. And you just sort of fall into the position that you're in.
We are getting a lot of questions about how scalable this plane is. Now, I understand that the idea behind it is that we should be able to fly commercially. So do you want to, this is a small plane right now that you're building, but how big do we hope to scale it?
Well, the purpose of this plane specifically is to go get the data so that we can change the regulation. Now, there are design features, through the, design codes in the computer that, we've used to design the airplane. So that would help when it comes to making something bigger. So the real purpose of that airplane is to, reset the regulation. It's not a prototype, although, we will be able to get information from it on design. So I think everybody is hoping that we'll be able to scale it up into something the size of the Concorde, eventually. So over to Alexandra for more.
Sure. Thanks, Nils. When we were first at NASA talking about how to design a demonstration aircraft and how large it had to be, we started trying to figure out, well, what's the smallest size that we can do in order to, keep it cost effective, but still be relevant to these larger future aircraft that we hope that we would have, small airliners, larger airliners, hopefully in the future. And so we did do some studies. We have a small simulator at NASA Langley where we can simulate these sonic booms and have folks from the community come in and listen to them. We have a little living room type setup, try to make them feel like they're at home. And we played back simulations of sonic boom sounds from the X-59, but also these larger aircraft type designs to see if people thought that the sounds were different or were more or less annoyed by different sizes. And we found that the size really wasn't a factor as long as the levels were about the same. And so we think that this is scalable, and the size of the demonstrator that we have is relevant for future designs.
Our friends at Goddard Space Flight Center are watching. This is an interesting question, and Ray, I'm going to start with you, but we'll see where it goes. Is there any new math, fluid dynamics, or materials that has contributed to these experiments in noise reduction?
I can't specifically point to, a new material, which I think is what the question is, that is being demonstrated on this vehicle. This vehicle actually is using a lot of traditional assembly methods, but certainly for future supersonic aircraft, the commercial supersonics program, which I was working on before I came to X-59, has been doing a lot of research in materials, lightweight materials for lighter aircraft, and also, improved high temperature materials for improved engine performance and lighter engines. So, for a future product, those kinds of technologies will be very important. And NASA definitely is working on those in addition to the X-59 demonstrator. I hope that answers the question.
Well, I'm going to follow it up with another one because I think this is interesting. Can you improve fuel efficiency during these flights to make these supersonic flights more appealing to commercial operators?
Right. I mean, I can try to field that one as well. You can join in if you need to. So one of the things that's neat about supersonics, and that kind of ties into a previous question about what's different about the Concorde, is the Concorde was built on I'm probably going to get this a little wrong, but 1950s technology, 1960s technology, and we have a lot better. We have engines with much better fuel efficiency now. So it's kind of a convergence of all kinds of new technologies that would make a next generation supersonic aircraft, more competitive and more fuel efficient than the past generations.
Well, we are almost out of time, so I'm going to end with one last question. I'm going to ask all of you the same question, and the question is, how important is math in this project? And how do you use it every day at your job? Because, there are students out there that are like, I'm never going to use this. But how do you use math every day? Nils, we'll start with you.
All right. Generally for me as the pilot, I don't use it quite as much as the engineers are going to use it. In order to become an engineer, I had to use it a lot. And the best part is, math is the language of the universe. So, it's what drives physics and chemistry and everything. It's what, it's the language that helps you translate everything that's going on. So if you're going to be a test pilot, you need to understand math. Generally speaking, I don't have to sit there and derive any equations or stuff like that. I let the smart people like Alexandra and Ray do that kind of stuff. So, but I do use it all the time. For me, it's usually more just simple math that we call it public math that you have to do, on the fly. But once again, when you're going Mach 2 and you got to do math in public, we always say that your intelligence goes down as your altitude increases and your speed increases. So, it's not so easy to actually just add things up when everything's happening really fast. But, math is hugely important, if you're going to do anything in a technical field and even non-technical fields. Like I said, it's the language of the universe.
Alexandra, how about you?
Sure. So Nils mentioned, the link between math and physics, and I think that's on the acoustics side. That's where the math comes in, because acoustics is really kind of a subfield of physics and understanding how, sound travels through the air and how, the ear receives the sound. And so math is really a part of all of that. The simulation tools that we talked about earlier of simulating the sound as it travels from the aircraft to the ground and understanding effects of the atmosphere and weather conditions. You need math in order to be able to, code up these equations to do the simulations. And math also comes in other areas where you may not think about it. When we're talking about putting together public surveys to understand how people react to these sounds, you need to understand how you would put together a test design, if you would randomize your sounds, or how you would actually do the analysis. And math is part of the statistics that we use for those analyses as well. So it's really embedded in kind of everything we do. So I would encourage everybody to continue studying your math.
Ray, what about you?
Yeah, I mean, I would have to agree. As an engineer, we don't even think about it. We use it every day. I have 2 teenage kids at home. They ask the same question: when am I ever going to use this? Something as simple as, say, making a drawing of the airplane. You're using geometry, or if you need to know the strength of the materials you're building the airplane out of. There's just math everywhere. It's just the language of engineering. So if you're interested in the aerospace industry, your knowledge of math is definitely going to be critical.
And I see that Nils did come up with a book suggestion, which I should have thought of. It's the Milestones of Flight book, from hot air balloons to Spaceship One. And my former colleague, Tim Grove, wrote it, and it can be found on the museum's website. I want to thank you all so much for joining us today. That was really a great chat. We appreciate you being here.
Thank you.
Great. Thanks so much.
I want to remind everyone that this video will be available on YouTube and Facebook right after the chat ends. Be sure to check out our latest STEM in 30, which is all about stealth and speed. We hope that you all will join us next week when we will be talking to pole pilot Roger De Laurentiis. And if you enjoyed this program, be sure to give STEM in 30 a follow on Facebook and Twitter. Thank you all so much for watching. Have a great day.